Okay, so we're very happy to have with us Jonathan Liu from MIT and John Martin from Pacific Northwest National Lab at Harvard. So without further ado, let's let them start with this discussion.
All right. Hi, everyone. My name is Jonathan, and today I'm very excited to tell you about some new work we have on Hamiltonian Decoded quantum interferometry, or HDQI for short. And before I start, I just want to give a shout out to my collaborators on this project. Sasha from MIT, Noah and Steven from Google, Alex from Boston University, and Yue here at EPFL. So HDQI is a talk about reductions. And just to make sure we're all on the same page, I'm going to start just by telling you what a quantum reduction is. So generally, reductions are how computer scientists formally reason about relating the hardness of one problem to the hardness of another problem. And what that means here is we say that we have a reduction from some problem A to some problem B, where if I have a solver that works for problem B, I can use a computer to build a solver for A. And if that computer is quantum, then we say it's a quantum reduction. So because of this, because we can turn solvers for B into solvers for A, we say that A reduces to B. And in that sense, A is easier than B if you have a quantum computer. Over the past couple of decades, people have found that quantum computers are perhaps surprisingly good at doing a particular type of reduction. And this is between optimization problems, which are like finding the maximum or minimum of some given function, to a decoding problem, which is in the setting of correcting errors. And I'll be more formal later about what that means. More specifically, it's a bit surprising because they're actually both classical problems. So I'm talking about reducing a totally classical optimization problem to a totally classical decoding problem using a quantum computer. There's been a good amount of history through this, starting with a work by Regev from a certain optimization problem called shortest vector in a lattice to a certain decoding problem called learning with errors. For purposes of this talk, I won't even tell you what either of those things really mean. This was followed up later on by Yamakawa and Zandri, who thought about max XOR sat, another optimization problem, to another certain type of decoding problem. And most recently, the general reduction between a max XOR sat problem to a decoding problem via this process called Decoded Quantum Interferometry, DQI, from Google. So as you can probably surmise from the title of this talk, we'll be focusing mostly on DQI, this last one. And so what I'm going to do is I'm going to tell you exactly what these two problems are, in case both of these are totally foreign terms to you. And then tell you how DQI works on those, and finally talk about how we generalize them to solve quantum physics problems. So let's start with max XOR sat. What is that? Here I'm going to specify to you a bunch of equations. I'm going to give you, each equation looks like this. It's like a mod 2 sum of Bij times Xj, and this is supposed to equal Vi. And we have m of these equations to you. So here I specify to you Bij, and I also specify to you the Vi's here. Your goal is to find a solution, which are these x's, such that you satisfy as many of these equations as possible. The reason that this is non-trivial is that there are m of these equations where we think of m as much larger than n. So this is an over-constrained system of linear equations, and you don't expect, in general, to be able to find a solution that satisfies them all. So instead, we'll just ask you to satisfy as many of them as possible. This is a classic, one of those NP-complete, like ridiculously hard problems. I'm going to write this in a little bit more concise notation, which will be more useful later on. So henceforth, when I talk about arithmetic, it's going to be mod 2 unless I say otherwise. Everything is binary. So x is now a length n vector, and these Vi's are also length n vectors, and I want these dot products to equal the Vi's. Once again, I just want to satisfy as many of these as possible. I can go one step further, and I can write this completely in just one matrix equation. So now B is this m by n matrix, and you should think of each of the rows as those Bi's previously. So this specifies what the system of equations is. And then V is what we call the target, so what you're trying to equal. And your goal is to find some x such that Bx is as close to V as possible. In other words, you're minimizing the norm of their difference. All right, that's max XOR sat. You have a matrix, vector product, you want to make it as close to a target as possible. Now let's talk about decoding. The decoding comes from the information theory field, where the goal is trying to ensure that we can communicate with each other reliably, even if the channel we're communicating through is a little bit noisy. So let's look at an example. Let's say Alice and Bob are talking on the phone in the old days, pre-error correction. Alice is a big fan of hiking, so she says, hey, you're going to the trail next week, right? Unfortunately, there's some noise in this channel, and what Bob hears is, you're going to the trial next week, right? This is unfortunate, because Bob has done some sketchy things, and now he has to go on the run instead of on a nice hike with his friends. This is not what we want. Instead, we'd like to come up with some protocol in order to make sure that whatever Alice's information is, she can encode it with some redundancy, so that when she sends it through the channel, even if some of the bits are corrupted, we can still recover the information she was trying to get reliably. So let's be a little more formal about what this means. Let's assume that Alice is sending a k-bit message, and she wants to add some redundancy to it. For example, a simple way is to just repeat her message like 5 times, and then if some of them get corrupted, at least Bob can tell by taking a majority vote what the bit probably should have been. More generally, you can try to pick some smart matrix, which we call a generator matrix or an encoding matrix. So this is an m by k matrix, where we think of m as a lot larger than k. In other words, you're taking this message of length k and you're embedding it into a much larger space. And the hope is that when you send gx over, this thing encodes some redundancy so that Bob has some method of recovering x reliably on the other side despite errors. And what this means is, as I pass through the channel, the gx is going to pick up some error e. Okay, so you should think of e as like some relatively sparse string of bits. Most of them are zeros, but there's a couple of errors here and there. Bob receives gx plus e, and then he has to run some kind of thing called a decoder, which from gx plus e extracts x out. In the case I previously said, where you just repeat yourself many, many times, Bob would just basically take a majority vote and then output what each of the outcomes of the majority vote is supposed to be. So that's all nice. But it turns out for the purposes of this talk, there's a dual picture of error correction and decoding that's more natural and convenient to work with. So let me define that for you too. So previously I said you take this message and you multiply it by this generator matrix to embed it into a larger space. Right, so the set of all messages, called the code words, is gx for all possible x. In other words, the space of messages is the image of G. It's this k-dimensional subspace of a larger m-dimensional space. Oh, I forgot about this. It's okay. 1 second. All right, forget you saw anything. Okay. There's an equivalent picture. Instead of saying it's the image of G as a k-dimensional subspace, you can specify it as just the kernel of some m minus k dimensional subspace. These two are equivalent pictures. And formally, the way you would do this is you would specify something called a parity check matrix, B transpose. This is an n by m matrix where n is m minus k. So as the kernel of an m minus k by m matrix, this is also some k-dimensional subspace of an n-dimensional space. So hopefully you can see that these two are equivalent pictures. But if not, just trust that this is another way to specify decoding. Where is that? Okay. So what does decoding look like here? Well, because you specified the code as the kernel of this matrix, if I start with some word in the code, y, and it gets some error, we know when we multiply by B transpose that B transpose y is 0, because y is in the kernel of B transpose. So all we have is B transpose times E. So actually the decoding problem becomes something that looks pretty simple. You take B transpose times E, and you figure out what is E. Now this won't work for all possible E. You should have this intuition that if I have an insane amount of error, like at some point there's just going to be no way to recover the information that I have. And indeed here, if the weight, that is like the number of ones in this vector E, if it's too large, then we're not going to be able to reliably decode. So our goal for decoding is, if the error is not ridiculously high, we can try to recover what the error is and therefore get our information reliably. All right, now that we have our notation set up and my clicker doesn't like me, let me give you a nice sort of viewpoint of what decoding can look like in terms purely of this parity check picture. So if all of that stuff sounds like nonsense to you, let's just take this as a mathematical definition. You can think of this decoding problem as the following. B transpose has a bunch of columns. E specifies to you a bunch of columns to add together. And the question is, I've added a bunch of columns together. What columns did I add? This is exactly equivalent to the question of what is E given B transpose times E. Given all this, I can now tell you pretty concisely of what DQI's reduction is. It's a reduction between this optimization problem of max K XOR set, or max XOR set, and decoding, where here I am decoding specifically the code whose parity check matrix is specified as the transpose of the optimization matrix. So here, this B, remember it's a tall matrix, it's n by n, it's an over-constrained system. And now I'm going to transpose it, and it becomes a wide matrix, which is exactly the form of a parity check matrix. And the claim of DQI, roughly speaking, is that if I can decode this code specified by B transpose, whose parity check matrix is B transpose, very well, then I can also output very good approximate solutions to the corresponding max XOR set problem specified by B. So let me be a little bit more concrete about exactly how DQI does this. So what's going on here is DQI takes the decoder as an input. We have to figure out, how to do the decoding. That's how reductions work. And then it's going to prepare the following state by running this decoder in quantum superposition. This state is a superposition over all possible solutions x, whose amplitude is a polynomial of f of x. So f of x is a function that measures how good your solution is. So if f is really large, then your solution is very close to optimal. And if f is really small, then your solution is really bad. And p, on the other hand, is any degree L polynomial that you like. So intuitively, what's going on here is if you can choose a really nice polynomial where it weights, it pushes down all the bad solutions to have very low amplitude and lifts up the solutions which are very good to relatively much larger amplitude, then if you measure this state, you're very likely to end up with a solution that's very good. In particular, we will basically just choose P to give very good solutions that we want. Now, here I want to mention that you can't just do any P. It has to be, it has a certain degree to it. And the degree of the polynomial is controlled by how well you can decode. In particular, if you can decode errors up to weight L, so L errors happened overall, then you can prepare this state for any degree L polynomial. This is important because the higher the degree, the better your ability to weight the amplitude such that you have higher weight on the good solutions. So as a concrete example, if you pick the polynomial to be some approximation of like a 1 over f of x to the high power or something, then you would expect that this polynomial will sort of concentrate your amplitudes towards solutions where f of x is
small.
Yeah, f of x is small. All right, I might have flipped it what it's supposed to be, but the point is you pick polynomials that you can pick polynomials that weight you towards good f of x, large f of x. All right. So given all this, hopefully we've convinced ourselves that quantum computers actually are pretty good at doing this reduction from a classical optimization, which is max XOR set, to a classical decoding problem. Given all this, you might have a natural question, which is, quantum computers are involved here. Can we introduce some quantumness into the reduction? In particular, can we reduce a quantum optimization problem to a classical decoding problem? I'd like to emphasize that we're still doing classical decoding here. There is no quantum error correction happening anywhere in this paper. So don't think of quantum error correction at all during this talk. So what is quantum optimization? Oh, well, okay. I was supposed to say yes. What is quantum optimization? Quantum optimization changes you from optimizing some particular function, like this matrix, to optimizing a Hamiltonian. And here, I'm going to just work with signed Pauli Hamiltonians. So these pi's are n-qubit Paulis, and these vi's are just plus or minus 1. And by optimization, I mean like finding the ground state, finding low energy states, finding a Gibbs state, those kinds of things for a Hamiltonian. In particular, our work, HDQI, is a quantum reduction between this type of quantum optimization with a signed Pauli, whose goal is to do things like find ground states or find Gibbs states, into a classical decoding problem. Now, in the DQI case, the actual mapping from the optimization to decoding was just taking the transpose. Right? You're given B as your over-constrained matrix, and the decoding problem is specified by B transpose as a parity check matrix. Here, we'll actually have to build some parity check matrix that depends on the Hamiltonian, but it's obviously not going to be something like transpose the Hamiltonian. That doesn't make any sense. So later on, I'll define to you exactly what this code is. But in essence, HDQI is reducing from optimizing this Hamiltonian into decoding a certain classical code that depends on the Hamiltonian. I should mention right off the bat that HDQI is actually a strict generalization of DQI. So anything that DQI does is also contained in HDQI. But there are things that HDQI does that is not contained in things that DQI does. So this mapping can be made very explicit. This is DQI, right? You take your constraint matrix B and this optimization objective. And what we'll do is we will just map this into a Hamiltonian. The rows of B become Z's, Z Paulis, and then the signs are encoded by the targets in the I here. And now, it turns out that finding the ground state of this particular Hamiltonian that we've constructed is exactly the same thing as finding this optimization, this optimum of the max XOR set problem. So for the remainder of this talk, I'm going to explain as clearly as possible what HDQI is and how each part of this works. So this is a schematic illustration of the entire algorithm. It's a bit overwhelming. There's like several moving parts. So I'm going to shine a little spotlight on each one of them and explain them in different parts so that it hopefully makes as much sense as possible. My goal, by the way, will be to try to teach like a basic simplified version of how this algorithm works. And I won't talk too much about the actual application it has, except for a little blurb at the end. If you're interested, I'm happy to talk more about it. All right, so what does DQI do as a starting point? Well, DQI is preparing this polynomial superposition over all the possible bit strings, right? Where this f of x here is measuring the quality of the solution. Now, because f of x turns out to be exactly the energy of the solution x in that Hamiltonian mapping from DQI to HDQI, you might imagine as a first step to generalizing the Hamiltonians that you might want to prepare some kind of state of this form. So now I'm summing over the eigenvalues, the energies of the Hamiltonian, and I'm weighting it by a polynomial. So I can perhaps choose this polynomial to have very high amplitude on, let's say, low energy states, eigenstates, and very low amplitude on high energy states that I don't want. And therefore, I can sample this and with high probability obtain a low energy state. That would be all nice. Unfortunately, this doesn't work because we have no idea, in general, what the eigenbasis of a Hamiltonian is. In DQI, the Hamiltonian was a classical Hamiltonian, so the eigenstates are just computational basis states. But here that's not the case. It's some like arbitrary eigenstate, and I have no idea what it's supposed to be. What are we going to do about this? Well, here's an interesting observation that uses some real quantum effects. Let's look at the maximally entangled state, or in other words, n Bell pairs. You can always write n Bell pairs as this superposition over the eigenbasis tensor its conjugate eigenbasis. And for purposes of this talk, it's like not super important exactly how this is defined, but it is like in some sense a conjugate of this state. This is great because if we can put the polynomial onto the Bell state instead, then just by writing of this form, we can approximately achieve that goal that we had originally, which is if we measure, we have a good eigenstate, a low energy eigenstate with high probability. So going back to this picture here, now instead of figuring out all the eigenstates that we need, we just throw in Bell pairs to the algorithm to start. We don't need to worry about the exact details of the Hamiltonian. Okay. Before I continue, let me give like a bit of intuition about how are we possibly going to make this state here. And this follows a bit from the DQI philosophy originally. What we're going to do is we don't know exactly how to just apply a polynomial of a Hamiltonian onto a Bell state. So instead, we're going to encode the information about this polynomial onto a simpler state, which we call the pilot state. Then we're going to attach it to the Bell state, and we're going to do some manipulations to try to transfer those amplitudes properly onto the Bell state, and then remove the pilot state register. In this process, it turns out that removing the pilot state register is non-trivial and requires a decoding step, which is where the reduction kicks in. So now let's look at that in more formality. In particular, let's talk about the decoder. In order to proceed, I have to now tell you exactly what this classical code that depends on the Hamiltonian is. And to do that, I'm going to give you a quick crash course on the symplectic representation. This is a very simple idea. If I take a Pauli string and I forget about what its overall phase is, I can always write it as some combination of x and z on each qubit. So if it's a y, it'll be x times z. If it's x, it's just x. If it's z, it's just z. Otherwise, it's just nothing. In other words, what Pauli I have on every qubit can be specified by just two bits of information, whether or not there's an x and whether or not there's a z. So we call this a symplectic representation. It just tells me whether or not there's an x and whether or not there's a z on each of my qubits. And what's great about this is that if you don't care about the phase of the Pauli, then this symplectic mapping takes products of Paulis into sums, mod 2. And remember, everything here is mod 2 when we do arithmetic, unless I say otherwise. Why is this the case? Because the x's will just cancel out if there's two of them. The z's will just cancel out if there's two of them. And they'll just add together, right? There might be some commutation, some sign that's picked up when you multiply Paulis, but we don't care about them. We just said they don't matter to us. Great, that's a symplectic representation. Now I will define to you a symplectic code, which turns out to be the code that we need to decode in order to make HDQI work. Remember that H here is a sum of signed Paulis, and for each Pauli, we can write it in the symplectic representation as simp of pi. This is going to be some 2n bit long string. Now I'm just going to stack all these strings. I'm going to arrange them together as columns of a matrix, and I'm going to call that B transpose. So this thing is a 2n by n matrix because there are n terms in my Pauli. And going in line with what I said previously about how we define codes, we will define the symplectic code of the Hamiltonian H to just be the kernel of this matrix we've written down, B transpose. In other words, B transpose is the correct parity check matrix we're going to work with. Let me jump back and just relate how the symplectic code works with this intuition I gave previously. So if you recall, generally in a decoding problem, we can think of it as I took my parity check matrix, B transpose, and I picked some of the columns and I added them together, mod 2. And your question is, which columns did I add together? Now here, the question actually turns out to be, I took some Paulis in my Hamiltonian and I multiplied them together. You have the final Pauli that I multiplied. Which Paulis did I multiply together? And through the symplectic representation, this turns out to be exactly equivalent to the decoding problem, because because multiplying Pauli's turns into adding things in this symplectic representation. And so this is why we can just think of the decoding problem as a completely classical issue. So for the rest of this talk, I'm going to focus primarily on the case when the Hamiltonian is a commuting Hamiltonian. And the reason for this is that commuting Hamiltonians are very nice. All the Paulis commute, and so you can simultaneously diagonalize the whole Hamiltonian by just diagonalizing one of the Pauli terms. And because of this, the Hamiltonian is like kind of classical in a vague sense. It's more classical than a fully quantum Hamiltonian. This turns out to be great because it simplifies our algorithm by removing one of the parts. Generically speaking, HDQI reduces the issue of preparing this polynomial state that I talked about before, applied onto the bell pair, into two problems. Both a decoding problem and a certain state preparation step. In fact, it's the pilot state preparation step. As it turns out, for a commuting Hamiltonian, there is no reduction needed for this state preparation step. We can always just do it efficiently. And for that reason, it makes it simpler that I can explain in more brevity here. Later, I'll return to show the full reduction that requires both decoding and a state preparation step. So what is the main claim here? Start with a commuting Hamiltonian. From there, I can write down a symplectic code for this Hamiltonian. This is a classical decoding problem. And the HDQI guarantee is, if you are able to find a decoder which can decode all errors in the symplectic code up to weight L, then I can prepare the following state using a quantum algorithm. This is literally just the previous state. This state here, the polynomial of the Hamiltonian times the Bell state, where I just trace out half of the qubits. Now, why would I be interested in preparing this particular state, this mixed state here? Well, as a starting point, and as the focus that we'll think about here for simplicity, polynomials, which have very high degree, are excellent at approximating general functions. And one thing it can approximate is an exponential function. And it turns out that if you can decode linearly many errors, by which I mean like L is linear in n, so it's a constant fraction of all errors, then you can choose a polynomial which is an excellent approximation to the correct exponential for this state here to be the Gibbs state. In other words, we can solve Gibbs sampling problems on certain Hamiltonians by reducing it into a classical error correction problem. Let me now tell you how the reduction works. How does HDQI prepare that state? The key fact here turns out to be a simple fact about polynomials in that they can be expanded in this symmetric form. So what I mean by this is you have some polynomial whose degree is, let's say, L, and I have a bunch of variables, zi, whose square to 1. You should think of these as the Paulis because they are. If that is the case, then if I apply the polynomial onto the sum of these zi's, so you'll recognize this as basically the Hamiltonian, then I can write this as a sum over some coefficients, wj. These wj depend only on the choice of polynomial. They don't depend on z at all. And then for each wj, you sum over all weight j vectors of length m. And you get this completely symmetric expansion of like z1 to the y1, blah, 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 zm to the ym here. That means, from this, we can write a very explicit form of this state that we're trying to make here. So as I said, the zi's are basically the pi's up to this phase vi here. And by using this symmetric expansion, I can now write it as a sum over wj's of this particular set of Paulis onto the Bell state. This is our goal. our goal is to figure out a way to like properly get this superposition with these particular Paulis onto the Bell state. If we get that, we're happy. So here are the steps to doing it. As I said, the first step is to say, look, that looks too hard, so we're going to try to encode the information about the polynomial into a simpler state, which we call the pilot state. So from the previous slide, the only information that we need from the polynomial are those coefficients, wj. So how do we do it? We're going to prepare a superposition over this wj's, and then the inside is supposed to be some like symmetric expansion, right? So we also need this like sum, the superposition, over all the vectors y with weight j. So this turns out to be a pretty simple state to prepare, because this is a superposition over not too many terms, and this thing inside is just a Dickey state. If you're familiar with that, it's just a very popular state that's well known how to prepare. Now what do? Let's tensor on the maximally entangled state onto a new register. So now I have 3 registers in my quantum computer. One A here that holds the pilot state, and then B and C which hold the 2 halves of the maximally entangled state. Now that I'm here, I need to figure out how to get those Paulis on. And this turns out to be not too difficult, because we just have to apply controlled Pauli operations from register A to register BC. So like if y1 is 1, I should apply v1, p1 onto. If y2 is 1, we should do that as well. If y2 is 0, we should do nothing, and so on. So this is just a controlled Pauli operation. So we can definitely make this fit here. Now notice where we are. We're here. We have this sum with a register with this y in the A register, and then this correct looking thing in the BC register. And if you compare to what our goal is, we seem to be tantalizingly close. All that's missing is this pesky little register A here. If we could just, get rid of this guy, we're happy. How are we supposed to do that? Well, to explain that, let me give you a little bit of a more concise notation. So I have this whole multiplication product going on here. Let's just collapse that together. So p underscore y is going to be like the product of the pi's specified by y. So if y1 is 1, then p1 is in there. If y2 is 1, p2 is in there, and so on. And the same thing for the vy of these phases. You just multiply the phases that are included in y. Now our states turn into this more concise looking form. And again, our goal is to get rid of this y8. If you've seen some quantum computing, you'll know that there's like a famous thing tricky thing about quantum computing. It's called uncomputation. This is what we're going to do here. We're going to figure out y from the other registers, and then we're going to add it to the first register, which turns, y plus y, mod 2 is 0. So that turns the entire first register to just 0, and then we can throw it out now. To do this, we'll exploit a fun fact about maximally entangled states. This is the fact that when you apply different Paulis to a maximally entangled state, you will take that state into different orthonormal states. In the case of just a single Bell pair, this is called the Bell basis. Different Paulis applied to the Bell state will turn it into orthogonal maximally entangled states. And actually, if I apply Pauli onto the Bell state, then this operation of turning it into orthonormal states can be realized very explicitly by just turning it into the symplectic representation of P. So this is like a 2n, a length 2n bit string, and there are 2 to the 2n Paulis. So each of these maps you to a unique bit string, which is the symplectic representation. Great, so let's apply this operation. And now we have a symplectic representation of this product of Paulis. But remember what I said before, the problem of decoding the symplectic code is I multiplied some Paulis together. Which Paulis did I multiply? Well, here I multiply the Paulis as specified by y. And I'm asking you to figure out y, which is exactly the thing I need to decode. And so, by the definition of B transpose, the symplectic parity check matrix, this is actually just, simp of py is actually just B transpose times y. This is just a decoding problem now. Take B transpose y and give me y, for y not ridiculously high weight. Great. Let's apply our decoder. We'll figure out y from B transpose y, calling the decoder in superposition. We'll use that to subtract out y in the A register. Now we have 0 for all elements of the superposition. And from there, we can discard it, and we're done. With this BC register, we just have to undo the thing that took us from the symplectic representation into that Pauli representation. And boom, that's our final state. We're done. So what happened here? We used this pilot state preparation at the start. We transferred its amplitudes onto the Bell state, except that that register had to be uncomputed out. By using the decoder, we successfully did that, and now we prepared the exact polynomial state that we want. So that's it for the commuting case. What about the general case? Can we go beyond commuting Hamiltonians? The answer is yes, but it turns out that when you have non-commuting things, you have to do much more work to prepare the pilot state. It's not this simple like superposition over Dickey states that I mentioned before. Let me give you some intuition as to why this is the case. The key fact that we started with previously to prepare this pilot state is the symmetric expansion for polynomials. Right? This is great. How does that work? Well, you have this standard polynomial representation, and then you insert the sum of the zi's. And now you have this like multinomial thing. And what you would usually do is expand this thing into like a full sum of products. You would collapse the products based on repeating terms because the zi squared equals 1. And then you basically like sort them into groups by their weight. But now, when I do this collapsing process, I have to move Pauli's past each other to cancel them out. But if they don't commute, I might pick up signs and weird things in doing this. So now this thing just doesn't hold anymore. Let me give you a super explicit example as to what happens in this case. So let's think about this Hamiltonian here. It's like xzx plus zxz minus x1. There's a nice representation of this called the anti-commutation graph. Here we just draw a graph. The nodes are each of the terms, and you connect nodes if they don't commute. So here we have some like non-trivial commutation relations, right? Like the xzx does not commute with zxz, and zxz doesn't commute with x. But x does commute with xdx. What happens to a simple polynomial? Let's consider just like an x squared, okay? Everything okay?
Yeah. You can just hold that.
So if these terms were commuting, then the expansion would yield this. It's like 3 plus some uniform expansion over all the two-body terms. But they're not commuting. And it turns out that the two of those like two-body terms just cancel each other out. And so we get a totally different polynomial that looks nothing like this. And our symmetric expansion just fails. Now, there's a long story behind how to fix this. But to save you the trouble, it's quite complicated. The general statement basically is, as long as I can prepare a certain pilot state which encodes a much more complicated structure of both the polynomial, which were previously just these coefficients, wj, and also the anti-commutation structure of h. So this pilot state, now that we need, doesn't depend completely on the Hamiltonian, but it depends on its commutation structure. That's the part that matters. If I'm able to prepare this like complicated state, and I can still do the previous decoding on the symplectic code for h, then I can go back and do exactly what I had before, which is prepare this polynomial, apply it onto the Bell state, trace out half of the qubits, and get this nice state that we want that can do things like approximate the Gibbs state. You might ask, you say this polynomial, this pilot state is some ridiculously overcomplicated state. Is this reduction vacuous? Like, is there actually a case for an explicit non-commuting Hamiltonian in which the pilot state can be efficiently prepared? and therefore the whole DQI process will yield something non-trivial. And it turns out the answer is yes. The general way that we prove this is we go back to the anti-commutation graph. Right? This is the thing that encodes the anti-commutation structure of our Hamiltonian. And our claim is that, well, it's a few things. The main one is that you can write this complicated pilot state as a matrix product state. If you're not familiar with what that is, it's a really nice family of states that physicists study a lot for classical simulation. And it has something called a physical dimension and something called a bond dimension. And if neither of these are horrendously huge, then we can prepare them efficiently. And it turns out so the scaling of the preparation is in the physical dimension, among other things. Because the bond dimension here is not huge, what matters is the physical dimension, and it turns out to be 2 to the size of the largest connected component of the anti-commutation graph. So this is a formal statement of if your Hamiltonian is not ridiculous, is not too non-commuting, like it's kind of close to commuting, by which we mean the anti-commutation graph doesn't have large connected components, then we can efficiently prepare the matrix product state representation of the pilot state and therefore run all of DQI and get the results out of it. I don't know if I said this before, but the cutoff is like log n for the connected components, because 2 to the log n will be like polynomial, and that's what we consider efficiency. I'm going to skip that caveat. All right. So to summarize, that was a spotlight for all 3 of these parts of HDQI. So what does HDQI do? In general, it takes 2 things. I need a pilot state that encodes the anti-commutation structure and the exact polynomial that we're trying to apply onto our Bell state. It takes a decoder that decodes many errors for the symplectic code of the Hamiltonian. And if it has these 2 things, it will transform an input source of Bell states, of maximally entangled states, into this polynomial state that we showed in a previous slide, such that you can choose it to approximate Gibbs states, ground states, etc. So just a quick note, as promised, on applications before I finish up. We here have a spectrum of things that we can solve and things that we can't solve, and also some things that we figured out how to dequantize. I'm not going to get into that in this talk, but roughly speaking, in the commuting case, we can provably prepare, let's say, Gibbs states at arbitrary temperature for a large class of Hamiltonians, which have a lot of relations to quantum error correction. Some of these, I think, are for the first time known to, these are the first known Gibbs samplers at constant or arbitrary temperature for those particular models. Now, interestingly, we also managed to dequantize and find an efficient classical algorithm that does all of these. So that's a separate contribution and kind of interestingly shows the gap between quantum and classical. It also gives a bit of foundation into the intuition I said earlier that commuting Hamiltonians are more classical and they seem to be easier to deal with. In the non-commuting case, we focus on this thing called a semi-classical spin glass, which is a somewhat physical-ish looking model that is kind of partway between a classical and a quantum spin glass, where we can provably use non-commuting HDQI to prepare its Gibbs states at constant temperature. And then there are stuff that are beyond HDQI's ability, and these can either be because the pilot state is too hard to prepare, perhaps because the commuting structure, the anti-commutation structure is too complicated, or because the symplectic code is just really bad and we don't know how to decode it very well. So to summarize, what we have shown in this talk is that we can use quantum computers to actually reduce from classes of quantum optimization problems into classical decoding problems, which is a very strange dichotomy and something that is hopefully quite interesting. In doing so, we were able to prepare some Gibbs states for both commuting and not two non-commuting Hamiltonians, which I showed in the previous slide. And interestingly, many of the commuting Hamiltonians, which we successfully got through, or successfully prepared Gibbs states for, are also dequantizable, which draws a nice boundary line and improves the sharpness of our understanding between the hardness of working with commuting versus non-commuting Hamiltonians. And finally, we worked with the semi-classical spin model as a exact instantiation, but I didn't speak too much about that. Okay. Before I go, I'm going to just mention a few interesting questions that I think come out of this work and are very intriguing to study. So one of them is about finding applications. I didn't have too much of a chance to go into what applications work and what don't work in this talk, but suffice it to say, a lot of realistic physical Hamiltonians that we care about are not something that like HDQI is currently capable or known to treat. It'd be very nice to see whether or not we're able to optimize or show we can optimize using HDQI some more realistic classes of Hamiltonians. It would also, on that front, be nice to see if we can go past this log n barrier from the non-commuting case and see if we can do HDQI with even more non-commutingness. That's not just like log n anti-commutation graph connected components. And finally, HDQI as a sort of new algorithmic connection between two fields can hopefully tell us more about complexity theory and the relation of different complexity classes. This is a vague suggestion. I'm not exactly sure how this will work, but I think it will be an interesting idea to explore. And just in general, this work is sort of a continuing a line showing that quantum computers have this surprising connection between error correction and optimization type problems, and I find it to be very fascinating to see how far we can push this frontier of that connection. All right, that's the end of my talk. Thank you very much for your attention, and I don't know if we have time for lots of questions, but I'll take any after as well.